Okay, now we're going to talk about real time, doing LFDCS in real time. Sorry. Okay, the real-time system that we've built consists of two pieces. One is software, one is hardware. The software piece is the LFDCS. The hardware piece is this instrument called the Digital Acoustic Monitoring Instrument, or DMON. It was originally built by Mark Johnson, Tom Hurst, and Alex Shorter at the Woods Hole Oceanographic Institution. It's since been redesigned by Jim Partan, Tom Hurst, Keenan Ball, and myself. It was redesigned because the original was really hard to manufacture easily, and so we had to change some things. But anyway, both of these systems operate exactly the same way. They both feature a low-power fixed-point digital signal processor that is a little computer. The computer is limited in its capabilities, but pretty useful for the things that we want to do with it. So it's programmable, so you can write code in C or assembly. It has flash memory, serial output, meaning you can communicate information from the instrument to whatever you plug the instrument into. And it has 3 hydrophones, low, a mid, and a high frequency, all tuned for low, mid, and high frequency. The LFDCS has been ported to the DMON, so it's not. This isn't. This runs. It runs conceptually the same software, but it's implemented in a very different way. It's not. There's no IDL. There's no windows to click. It's all running inside this digital signal processor. So it uses the same pitch tracking algorithm. When it does the discriminant function analysis, same as before. It conditions the spectrogram, gets rid of tonal and broadband noise, does the pitch tracking, and does the discriminant function analysis using a call library that's loaded onto the instrument. And then those pitch tracks and classification information are passed to whatever platform it's attached to. And then that platform's responsibility is to get that data through the Iridium satellite system and to shore, where we can do something with it. Okay. The LFDCS and the DMON and the DMON2 also simultaneously records audio, and you can record at most any sampling rate you want. The LFDCS that we use samples at 2 kilohertz. For the DMON2 continuously. For the DMON1, duty cycled for buoys and continuously for gliders. Okay, and I have here a DMON2 board, which you guys can see, and a hydrophone, which I'm going to pass around to the folks here. If you look in the hydrophone, there are 3, you guys can see, there are 3 cylinders inside, a low, mid, and high frequency cylinders or hydrophones.
Careful.
It's not the end of it. You won't hurt it. It's fine. Sorry, I shouldn't have said that.
Don't break it.
Okay, you've seen this slide now a gazillion times. But again, the point here is that we can do the pitch tracking, only now those pitch tracks are useful in themselves for aiding us in being very confident in what species is there. So as before, on the DMON or DMON2, we're creating that spectrogram at the top, and then we're doing the pitch tracking algorithm. And you might remember at the very beginning, I said you don't even need the spectrogram anymore. Well, that's good, because sending that spectrogram home via Iridium would be really, really slow and really, really expensive. Satellite communications are basically like you used to send emails back in 1998, right? I don't, some of you are too
We
young
were
for this.
alive,
Okay.
yes.
So you remember the modems that when you connected, they would make all this awful racket, and they would run at about 2400 to 9600 baud, which is the communication speed. Well, that's basically what we have for satellite communications right now, that you can use at sea reliably. So we can't send that spectrogram. We can't send the audio home very easily or inexpensively. But we can send pitch tracks home because they're really small. They're compact representations of sound. You notice that in the spectrogram, there's not that much information. There are 3 Finwell calls and 2 Saywell downsweeps in this sea of gray. But we don't really need to know anything about the sea of gray. We don't have to take all the time and money and energy to send all that information home because there's really no information in it. We just want to know about the calls. And so this idea of doing the pitch tracks and then just sending the pitch tracks home is really, you can think of as almost like a data compression kind of, or data extraction type of exercise. But what I want you to notice is that the pitch tracks are faithful to what's going on in the spectrogram. So much so that you can get rid of the spectrogram. If you get good at it, you can throw the spectrogram away and just look at the pitch tracks, and you can know what's going on. The classification information is great, but anyone that's someone like Julianne who spent years doing this just looks at this and says, yeah, there are 2 Saywell downsweeps and 3 Finwell calls. It's easy. And she didn't have to listen to the audio or look at the spectrogram to determine that. So that's the trick here with doing real-time detection, is we're just looking at the pitch tracks. So we've taken the DMON2 and we've integrated it into several autonomous platforms. And each one of these we've written about our experience with them. So the Slocum Glider is a mobile autonomous platform. It's a long endurance platform. It can stay at sea. My gliders stay at sea anywhere between 3 or 4 months at a time. Moored buoy is if you want to monitor in one place for a long period of time. These moored buoys are specially built. They are ruggedized in such a way that we can operate them for at least a year at a time before we have to go out and refurbish them and change batteries. They're purpose built to be very, very quiet so that we aren't listening to clinking and clanking of the platform. We're actually able to hear whales very far away. The third one is the Wave Glider. It's a different kind of autonomous platform. If you're feeling like you need a sleep aid, I really recommend this paper about the Wave Glider. It's not that exciting. And what's interesting about that paper is it basically says the Wave Glider is not a very good platform to do low frequency monitoring. So there, I told you. You can use it to sleep better. So, and then the last is just in the past few years, we've implemented the DMON2 in a what's called a profiling float. And that's a very long endurance platform. It's meant to actually be expendable. It operates for a couple of years at a time and then basically scuttles. And if you want to hear more about that, for you that are here in this room, come see my poster on Tuesday. So all of these platforms sort of work in the same way. The DMON2 does its thing and it passes off detection information to the platform, and then the platform sends that information home. So the Slocum Glider, Moored Buoy, and Wave Glider all work in the same way. Every 2 hours, they make a phone call home and they send all that pitch track and classification information home. Remember that mean spectra that I talked about very early in the day? It sends that, it samples that every 30 minutes and sends it home. And that's it's a great representation of the background noise. There's a bunch of status information that gets sent, as well as any platform information. From the glider, Slocum Glider, we get tons and tons of information about what the glider's been doing over the last 2 hours. But at the very least, we get platform location and status information. All that data goes up through the Iridium satellite system to computers in my lab gets processed immediately and then gets displayed on the robotsforwhales.hui.edu website that Julianne's going to walk you through very shortly. Once the data is there, we have lots and lots and lots and lots of pictures of pitch tracks like this that an analyst like Julianne just goes through minute by minute and determines what species are present. Here's a nice depiction of a whole bunch of right whale up calls. You'll see underneath some of the calls are some numbers. Well, you'll know what those numbers are now. It's the call type and the Mahalanobis distance. And so the analyst can use that information to sort of make a determination of how legitimate is this pitch track.
We can verify, we answered Robert's question earlier about the call tape.
Right,
Mahalanobis
right.
distance sent
Robert
to, yeah.
asks about what Mahalanobis distance cutoff do we use? We use I don't think that the classification information is shown if the Mahalanobis distance is over 3. But you'll notice there's a couple of calls here that don't have classification information. So you might think, well, the LFDCS missed those. Well, they're probably classified as right whale up calls, but have a Mahalanobis distance over 3. But that's okay because we have a human in the loop here. And the reason the human's in the loop is to drive our false detection rate to 0 with these platforms. So when a person is looking at these, they can say, okay, well, some of these are classified, but I know with a Mahalanobis distance of 3, I'm going to miss some things. If you, we didn't show this before, but or at least we didn't point it out. If you looked at the Mahalanobis distance of the exemplars of the call types 5, 6, 7, and 8, and 9 are right whale call types, there's a percentage of them that are actually greater than 3 for Mahalanobis distance. What that means is that legitimate calls can have a Mahalanobis distance over 3. That's just the nature of the beast. So some legitimate calls could be missed if you said the only right whale calls out there have to be less than Mahalanobis distance of 3. So even though we have this cutoff, the cutoff is really just kind of setting where our missed detection rate is. But in this case, there is no missed detection because Julianne's going to be looking at all the calls, whether they're classified or not, they're on the screen in front of her. So she gets to evaluate them. And so she would look at these calls and say, yeah, that's definitely a right whale call. It's classified. It's there's no noise around it. You know, it's got a nice shape. So that's a right whale call. This one's really good too. So that probably means that these other ones are right whale calls too, even though that they're not classified. And that's okay because we are going to rely on Julianne's expertise and judgment. And that's the nature of the beast with passive acoustic monitoring analysis anyway, is it's a subjective distance anyway. Okay, so once the analyst goes through and decides, yeah, during this period of time, there were right whales or there are sei whales or whatever, that information gets distributed through a number of different channels. One is their summary tables on the Robots for Whales site. If you want, you can get text messages. Most people get email messages about what species are present for what platform. And then it goes out to a bunch of different, or I shouldn't say goes out, lots of applications come into the Robots for Whales system, sort of in the back end, and scrape data out of it. And so Whale Alert the Whale Alert app is one, the Coast Guard's CG1 View, New York Aquarium is doing this, the Whale Safe program on the West Coast, Mysticetus, I think
not live, but we do.
Right,
Yeah.
Packham does it. Whale Map in Canada, Hanson Johnson's system. So lots of different places come in and grab data from Robots for Whales. Okay, so that's an overview about how the system works. I want to just discuss for a second a peculiarity about what data gets sent and why. So you notice that this says a subset of pitch tracks and classifications. We don't send all of the pitch tracks home. The reason we don't send all the pitch tracks home is because if you had a humpback whale singing right next to your glider, that's going to be really expensive because all those pitch tracks are going to go through the Iridium satellite system, and Iridium's going to rack up the charges because you're going to be on the system for a long time. And so you might have if you have a humpback singing next to your glider, all month long, you might have a $10,000 Iridium bill. So in order to avoid that, we limit the pitch tracks, but we limit it in a particular way. I was going to say a peculiar way, but I think it's just particular. So during any given hour, at most 8 kilobytes of pitch track data is sent to shore. So at the start of the hour, pitch track transmission from the DMON2 is turned on. And you basically, for every pitch track you get from then on, you just increment a counter for how many bytes the pitch track data consume. And when that counter gets to 8 kilobytes, you stop transmission. You turn off the pitch track transmission. Okay. The transmission will be turned on at the start of the next hour. Right? So during any given hour, 8 kilobytes is the most that's going to be sent. So that nicely limits how much Iridium time we're going to be using. For our buoys right now, we spend about $500 a month on our Iridium bill, and no more because it's limited in this way. So what that means is that in a noisy environment, so that humpback whale that's right next to our glider that's blah, 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 singing away, pitch track transmission might last only a few minutes. That whale might make so many tonal sounds that you just, within a few minutes, you've reached your 8 kilobyte limit, and that's it. And for the rest of the hour, you get no data. In a very quiet environment, you might make it to the next hour without ever having reached the 8 kilobyte limit. And that's a good, that's a good monitoring situation. Whereas the humpback whale singing scenario is kind of stinks because you're missing out on a lot of the hour. Okay. So you'll be able to see this when Julianne's going to go through the website. But one of the things that's on the website is this daily tally table. And I picked out one for a West Coast buoy, so it only has blue and fin whales on it. But in the tally table, we've broken out the data in what are called tally periods. Tally periods are nominally about 15 minutes long. The duration column here shows how many seconds are in each tally period. For gliders, pitch tracking gets turned on and off whether based on whether the glider is surfacing or not. And so you'll see variation in the duration of the tally periods. But for the buoys, it's 900 seconds solid. So you get one row for every tally period, and it'll tell you the total number of auto detections during that period for the different species. In this case, just blue and fins. Okay. The other is how many pitch tracks have been sent that are not classified as blue whales or fin whales. So it could be another species. It could, if humpbacks are calling, they don't get classified, but you can see them in the pitch tracks. Julianne will show you some examples of those. You might get a high number of others for that. Also, if there's some noisy thing going on, you might get lots of other pitch tracks. So we use that sometimes as a metric as how well we're monitoring. But what I want you to notice is in the tracks column, that when you see a PT, that means there have been pitch tracks sent during that 15-minute tally period. Okay, so you notice that not all tally periods have pitch tracks associated with them, and the reason is because you've reached that 8 kilobyte limit and you've shut transmission off. Okay. So when we're monitoring really well, every single one of the rows, every single one of the tally periods will have a PT in it. If you're not monitoring very well because there's some interfering noise that's producing a lot of other pitch tracks, you won't see a lot of these rows won't have PTs in it. Okay. Okay, just to give you a sense of what platforms are out there. This is a map of the U.S. And this is where all our buoys are deployed right now. So one off of Martha's Vineyard, two off of New York, although one's not working right now. one off Atlantic City, New Jersey, Ocean City, Maryland, Cape Hatteras. Next month, we'll be putting in new buoys off of Norfolk, Virginia, and Savannah, Georgia. We also have a buoy off of Santa Barbara in the Santa Barbara Channel. And this is no longer planned. This is deployed. We deployed, I think, last month, a buoy off of San Francisco. We also operate gliders. I have a fleet of 5 gliders. 3 of them are in the water now. I have other partners, Rutgers University, University of Maine, and shortly Stony Brook, and University of South Carolina and Skidaway will have a glider as well. Operating on the East Coast, all doing the same thing, sending pitch track data home. We have colleagues in Canada, Kim Davies and the ocean tracking team use gliders in the Gulf of St. Lawrence and off in Nova Scotia. Quite a bit during the summertime. They do a lot of glider deployments. And then just on the West Coast, we don't have any glider work, but a lot of the data all of the data go through this WhaleSafe program. So if you go to whalesafe.com, you'll see some of our data being used to try to manage, reduce the risk of vessel strikes in Santa Barbara Channel and near San Francisco. The East Coast data is mostly focused on right whales, and all of the right whale data go to the US government and are used in what's called the Slow Zones for Right Whales program, which is a program of voluntary ship speed reductions along the US East Coast. So when right whales are heard, these slow zones go into place and mariners are encouraged to slow down to 10 knots or less around the area where right whales have been detected. In Canada, there's a lot more teeth. The detections, the right whale detections are used for mandatory ship speed restrictions, as well as fishery closures as well. And this is, I think, my last slide. This is just the most recent, I think, the most recent slow zones map. In all of those yellow boxes, all but one of them were instituted from acoustic detections from our platforms, gliders and buoys. So now is the time when right whales are, as Jen said, are kind of spread out along the US East Coast, and we're seeing that in the real-time data. So that is all I had.
We have a question.
Okay.
Online. Can you buffer the pitch tracks during a noisy period and then send the portion over 8 kilobytes during the next quiet period?
Oh, clever. Yes, I mean, yes, you could do that. That's a very clever suggestion. You just have to be really careful about when the next quiet period is. You'd have to be smart about when to invoke that and when not. Just because you might not get another. It might be some time before you get a quiet period, in which case you might have a pretty big backlog of data to send. So, and again, this system is meant to be real time. We call it near real time because you don't get the detection information within seconds of it being produced, but you get it within a few hours of being produced. That kind of a scheme might delay that for some time. So I'll think about that. It's a good idea.
Great. Yeah.
Any other questions? If not, I'm going to hand it over to Julianne, who's been doing, Julianne's monitoring 7 platforms right now, and she's been working all day today to try to get caught up from traveling.
We do have a question.
Oh, go ahead.
How much is C versus ideal code
How
on a
much?
desktop? Oh,
How much in terms of?
is any of the code of LFDCS written in C, I think, on the desktop version? I think, is that the question? Did I get that right? Yeah, okay. So is there anything written in C on the desktop version? of
Yes.
LFDCS?
Yes, all of the pitch tracking algorithm, all of the spectrogram conditioning, really all that's done in IDL is all the viewing and interacting, but the actual processing is done using C code that's linked into IDL.
So heavy lifting is C. Is the heavy lifting C in C code?
Yes, when you run reformat, detect, classify, IDL is doing the Fourier transforms to build the spectrograms, but all of the LFDCS processing to do the pitch tracks, to condition the spectrograms, no, that's done in IDL. To actually generate the pitch tracks, that's all, and do the discriminant function analysis, that's all done in C code.
Is that C code available?
It could be. I've never distributed it just because I'm. It could be. I'll leave it.
There's a smiley face, so we'll leave it as a smiley face back. Here's a lot of data. I understand that, and I can tell you that
But why would you need the code? You have the LFDCS.
it works great.
Yeah, you have a manual and you have Jen to call. Why would you want the code?
Oh, no, Max. No, Max. Oh, we should
Oh,
mention.
Okay, so so why is it that we have that this is done at Max? So it was to be very honest. The LFDCS was written for and by me, and so some of the less user-friendly aspects are because I never anticipated that this would be used by other people. And then Jen came along and
I was like, this is so great. Look, everybody, look what we can do.
Yeah.
And then we created.
and she was very tolerant of it not being very user-friendly. So any user-friendly aspects of it are really because of Jen. So that's a funny way of saying I use Mac, so it was very easy to implement it on a Mac. It can be implemented on a PC, except one of the challenges is that the audio playing aspect of the LFDCS is not implemented in IDL. And so I had to write some separate code to actually do the playing of audio, and that hasn't been done for the PC yet. So if you're really good a PC programmer and you know how to write and see some routines to actually play audio, let me know, and we can get this ported over to PC. I just haven't had time to delve into that.
2 more questions.
And I guarantee you it's cheaper to go out and buy a Mac than it will be for me to give you the code and you to reproduce the LFDCS on your own platform with your own code. It took me years to write all this, so just go out and buy a Mac.
So the new Macs have the M1 processor. Will the C need to be recompiled?
I don't know.
And then the other question, can we just run it on Linux or PC?
Linux has the same problems. You can't, I don't know how to play audio on a Linux. So it might be easier, but again, if I just haven't had the time to do that.
So Macs, it is.
Max, it is. I mean, that's the short answer. It's cheaper for you all to buy Max than it is for me to spend a week doing it. I guarantee you, with my institution's overhead. So it is what it is.
Yeah.
Well, you can just be like Jen and ask me for an old Mac, right?
Yeah, and I think they're new, but they are new for us, but they're like 6 or 7 years old. It's
So
great.
you could, so what I've done is I've just asked my department, the biology department at Hui, does anyone have an old Mac that they're not using anymore? And I got 3 or 4 old Macs, one of which is perfect for doing this, and I refurbished it, and now Julianne has it. So you don't need a new Mac. IDL, an academic license for IDL is like $420, which is in our world is pretty chump change in terms of grant dollars. And then you're cooking with gas. I mean, to refurbish a Mac, to just wipe the hard drive, clean up the operating system, takes about an hour. So I had Julianne's Mac all set up from getting handed like this dirty used Mac to like an actual nice cleaned up, wiped system with LFDCS on it took a couple of hours. So I bet you can find Macs and get them working no problem easily.
Yeah, I think we have one but the one you were working on was like 13 years old. It was a 2008 computer
2008.
and still running. So they last a long time too if you do invest in them.
Yes.